Professor Yamei Zhang is a professor of the School of Material Science and Engineering at the Southeast University, China. And she is also, I'm very proud to say, an affiliate professor of the University of British Columbia. So we are very proud to have, Yamei as our affiliate professor here at University of British Columbia as well. She's the director of Nanjing Institute for Intelligent Additive Manufacturing and an official academic partner of Holcim Group on 3D concrete printing. A well-known expert on additive manufacturing, Dr. Zhang also serves on the editorial board of Journal of Cement and Concrete Composites. Professor Yamei Zhang. Let me stop share.
Thank you, Nami. Thank you for your kind introduction. And also, thank you for inviting me to share our research on 3D printing concrete. So I will talk about the 3D printing concrete progress in my group and also the application of 3DPC in China. First, I will briefly introduce the CSI China chapter. The CSI China chapter was founded in 2002. The headquarters was located in Hong Kong, China. Now we have 111 members in total. The current president is Professor Xiangling Gu from Tongji University. So the mission of CSI China chapter is to carry forward the purpose of CSI, that is to promote education, technical practice, scientific research, and to improve the design, construction, use, and durability of concrete structures and products by collecting, sorting, and publishing relevant information. So now we also have many activities so far in China. For CSI China chapter. For example, we organized the CSI certification in China, concrete laboratory testing technician level 1 since 2011. And every year we also attended the CSI leadership training since 2016 and attended CSI Spring of Fall conventions on behalf of China. So 2 years ago, we established the CSI Tongji student chapter. So we also could organize some academic conferences and communications in China. So here are some photos showing the activities. So now I would like to move on to my presentation on 3D printing concrete. In China, we are now facing the lack of laborers in construction industry. So we need to use advanced technologies such as 3D printing technology in this industry. So we all know that for 3D printing concrete technology, there are many advantages when compared with cast concrete. The typical one is there is no formwork needed for 3D printing concrete technology. Now use this technology, the designers will be very flexible in their design. It's also labor saving. And yes, there are many advantages like safe construction, high construction efficiency, low cost, and low carbon footprint. Okay. For 3D printing concrete technology, because of its spatial printing technology, so the requirement for material is quite different, especially for its fresh properties. So for 3D printing, we need to first pump the material to the container, then extrude through the nozzle. After extrusion, good buildability is needed. So for 3D printing, so for mixed design of 3DPC, it's the first thing is to design good printability fresh concrete. So this is a very basic requirement. But now, because of this special technology, there is a limitation on the material use, especially the lack of coarse aggregate. The currently printed concrete projects, they mainly use mortar, but not concrete with coarse aggregate. And yeah, so we have done some research in my group about the mixed design of this spatial technology. So far, we can find that from many literatures that in fact, there is no design, or maybe many researches are based on their experience by, try and error test in the lab. But this is not good, for develop this technology. Here are some statistics about the current research about 3D-PC. They use different materials like silicon film, fly ash, bentonite, and other materials to adjust the printing property of 3D-PC. But if to better promote the technology, we need some other model, especially maybe some theoretical model is better for us to use this technology. So we can find some rheological model like these three models shown here. For these models, mortar is considered as two-phase material composed of aggregate and paste. So we can see from this equation that quantitative relationship is established between aggregate and paste. And what's important is this model is independent of the specific raw materials we use. We just use, for example, the state of the aggregate and the rheological properties of paste. Okay, so in my group we have we tried to use excess paste theory to do the mixed design, because for the 3D printing concrete, the paste thick around packing the aggregate is a very is a key parameter for designing the concrete. It determines the flowability, the extrudability of the concrete. So excess paste theory or excess paste layer thickness, this is a very important parameter that can reflect not only the volume fraction, but also fineness, shape, and particle size distribution of aggregates. So we have used this method to design 3D printable concrete. So we use different mixtures. You can see different materials to prepare the concrete. But if we can design the excess paste thickness and know the paste flowability, you can see the design, the properties of printed mortar or concrete, they have very similar printability, and of course also very similar rheological property. Okay, this is a relationship between the we want to use this relationship to predict the static yield stress, because static yield stress is a very important parameter that determines the buildability of 3D printed concrete. So we find this exponential relationship between the ratio of yield stress of mortar and yield stress of paste. They are exponential relationship with the excess paste layer. This can be used to design the mixture of concrete. Okay, and also we developed a modified COST model to better predict the yield stress of mortar, because only when the yield stress of mortar lies between some spatial range, this concrete can be printed. Okay, but in the lab, in some labs, they do not have a rheometer to test the rheological properties. So we try to find the relationship between the yield stress of the material and the flowability. It's very easy to test the flowability of fresh concrete. So we also find the good relationship. Then this will be very easy for us to use this relationship to design 3D printable concrete. Okay, next I will like to introduce the 3D printable concrete with coarse aggregate, from some published papers and also from our experience. Here are some elements exposed in the air for 1 or 2 years. We can find some cracks. So cracking is an issue now because we mainly use mortar. So it's quite necessary to use to print concrete with coarse aggregate. So the reason is, very, very simple. I will go directly to our research. And in our lab, we have printed concrete with coarse aggregate. The maximum diameter of coarse aggregate is still not too large. It's about 5 to 10 millimeter. And this is the printing in our lab. So you can see that from this picture here, you can see there is no visible interlayer interface or defects between the layers. That means the printing of this concrete is successful. And for the concrete with coarse aggregate, it's the paste to aggregate. The paste to aggregate ratio is a very key issue that determines the printability, the stability of the printed filaments. For example, here on the left side, you can see when the paste aggregated ratio is too high, it's not stable. It's not what we want, okay? But when the ratio is so we wanted the very satisfactory 3D printed concrete. And we also investigated the ratio of coarse aggregate to the total aggregate. So when we can see when the coarse aggregate content is too high, we can find the defects. This is not so satisfactory, but at the proper coarse aggregate volume, we can get a very good surface of the 3D printed concrete. Okay, here are some mechanical properties of 3D printed concrete with coarse aggregate. We compared with that of cast concrete. And this is, we found from published papers that, for some research, they showed that the strength of 3D printed concrete with coarse aggregate is normally smaller than cast concrete, but in our investigation, we found that we got higher mechanical properties of 3D printed concrete when we use coarse aggregate. It is because the compatibility of printing parameters and the rheological properties of 3D and for 3D print concrete, there is no protection from formwork after casting. So that means the environment will greatly affect the properties of concrete. Okay, yeah. We investigate the concrete cured at different conditions, humid, dry, and wind. Okay, here are some typical results. We find that 3D printed concrete is more vulnerable to dry and wind when compared with the cast specimens. This is very important for us because some projects are completed on site. That means the hardened properties of concrete will be not as good as expected. Okay, we found the relationship between the mechanical properties and the internal relative humidity. The result is the early curing condition is quite significant to the strength development of 3D printing concrete, for which early curing is often not available for the on-site 3D printing. The reason for this is for 3D printed concrete, we got more connected pores that in fact affect the mechanical properties. So now let's move on to the application of this technology. So far there are many applications for 3D printing concrete. I will not go into details about these projects, but because there are now different application methods, on-site 3D printing or on-site fabrication of 3D printed elements in the factory. So, but the difference between these two technology I want to emphasize is for on-site 3D printing, the printing process is influenced by wind, temperature, and humidity. So the on-site curing is the issue, but for the fabrication technology, printing quality can be guaranteed in the factory. Okay, I just want to show you a typical application of the 3D printed fabricated building in Nanjing. This is the calculation of about the heat transfer is the joint work between my group and Hongkong-Zhuhai's team at the University of Tennessee. The wall is 3D printed and fabricated on site. We consider the heat transfer between indoor and outdoor, and compare the heat transfer between two typical buildings. This is the 3D printed wall system. This is a system for comparison, a conventional area-edged concrete block wall system. Okay, we compared the temperature outside on the surface of the wall in the wind. In summer, you can see the temperature on the surface is much lower than the traditional one. Okay, and this is a wall heat flux of the building. We can see that the heat flux of this 3D printed wall system is about nearly 70% lower than that of the counterpart. And here is the process. This is 3D printed elements in the factory and on-site construction. This is the final buildings. We have three such buildings here. And we also have some other applications of the 3D printed technologies. That means fabricated in on-site using 3D printed elements in the factory. So here are some typical pictures. Some projects we have finished, and some other use of this technology. And in China, we also have some other projects by different groups. This is one. What I want to mention is this is very interesting because you can see the vertical steel mesh reinforcement is used. Then a special nodal is a fork type of nodal is used to spread concrete from two sides of the steel mesh. And this one is the work from Professor Guo Ma's team. This is a Mimik Jojo bridge. The bridge is built in his campus, in their campus. The main structural elements was produced by casting concrete in a 3D printed permanent formwork. Then the concrete was cast inside the permanent formwork. Okay. And another building is, this is a building by the China State Construction Technology Center. The wall was printed on site, but you can see the reinforcement and some pipes, then concrete was cast, okay? But the beams and the columns and the floor was cast concrete, but not 3D printed concrete. Okay, this is a very recent work from Professor Wei Guoxu's team from Tsinghua University in China. They used the three robot printers to print. These robots were installed on the lifting platform. Okay, for this building, there's no any steel reinforcement. The roof's also printed, but it's installed after printing. Okay. Finally, I want to talk about the challenges of this technology. The first challenge is the 3D PC mixed design, because current mixed design of conventional concrete is not suitable for this 3D printed concrete because printability is the first concern in the design of 3D printable concrete. And in the meantime, we also need to consider the strength, deformation, and durability when we design the concrete. Another challenge is about the 3D printing with coarse aggregate. We first need to develop some printing system because the system for printing coarse concrete may a little bit different from for printing mortar, and also some suitable printing technology. And we need to also have favorable surface treatment of the printed concrete with coarse aggregate. And another issue is about the reinforcing of 3D printed concrete. Now there are already some technologies, but so far these reinforcing technologies are not very satisfactory because the reinforcement can interfere the progress of 3D printing. Okay, so maybe we need to develop some new structure that is independent of traditional reinforcement. Okay, and also we can develop some new reinforcement approach that can coordinating 3D printing of concrete and the layout of reinforcement to reach high efficiency of this technology. And one important issue is the standards of the technology needed, because when we want to push the application, the standards is always needed. Okay, we need to develop testing methods, design codes, and quality acceptance for the 3D PEC elements of structures. Okay, so I think this is all I want to share with you. Thank you for your attention.